keep in mind for this particular chapter. One, you have to be comfortable with writing equations and balancing. All right. Now, when it comes to writing equations, you have to be familiar with what is the symbol for each and every one of the elements that you're working with. Now, mostly you work with a lot of elements that are within the first 20, like within the first 20 atomic numbers. Occasionally, you have a few other elements that are out of it, like lead, copper, silver, all right? But this writing a formula and being able to look at the chemical name and know what the formula is all done in your class 9 itself, all right? You do need to go over it if you're not comfortable with it, because writing formula and writing equations, and more importantly, balancing equations, is literally the entire key to your class 10 and 11 and 12 if you choose to continue in chemistry. Okay, so without being able to write formula, without being able to balance equations, it's going to be extremely difficult for you to get comfortable with the subject. So I would definitely suggest that if you're not, go back to your 9th standard, refresh it, and then get back to your 10th standard. Today we're not going to be covering that. We're just going to go directly into the questions. So I'm going to share my screen. There, the first set of questions are going to be all MCQs. I'm going to give you about 2 minutes or less, probably 1 minute for every question. Mark the answer in your book, in your notebook, all right? And then we will discuss each and every question and answer, and I'll give you an explanation as to why. Now, besides knowing the formula and writing balancing of equations, the other key thing that you need to know is that you have to be able to know what is the observation. So a lot of the questions that come from this chapter is related to what do you observe. And the one biggest mistake that students make when this question comes is they just write an equation. All right. An equation is not the answer for a question that says, what do you observe? All right. So when the question asks, what do you observe? The key things that you are expected to write would be, is there any sort of a color change? Is there any kind of a gas being liberated? And does this gas have any characteristic features? Maybe it has an odor, maybe it has a color, maybe it has a specific test that can be performed to understand that, oh, if this is a colorless, odorless gas, then this is how it will work. All right. So it is important that you are familiar with how to observe, or what are the observations related. So like I said, the key things when it comes to what are the observations related to a reaction would be, is there a color change? Is there appearance of a precipitate? So a precipitate is basically when you see the appearance of something solid. So when you mix two liquids and at the end, if you get something that's solid, that solid residue that is appearing is called as a precipitate. The precipitate may be white, the precipitate may be colored. It depends on what the kind of reaction is. All right. So you will find that questions that are related to observation, anything related to observation, is going to be based on, is it color change? Is there a precipitate? Is there a gas being liberated? Sometimes there might be some sort of a temperature change. So it could be exothermic or endothermic. But anything that is an observation-based question means you need to be able to tell what are you visually seeing when it comes to the change. All right. So let's just get right into it. For all those of you who just joined in, please keep your mics on mute and your cameras off for now. We're going to dive into the questions, and as we work our way through the questions, I'll keep giving you explanations as well. If you have any doubt while I'm giving an explanation, there's a raise your hand option. Please go ahead and raise your hand or drop the question directly in the chat box. All right. Okay, let's get started. We're going to start with MCQ style questions, because I feel that while these are easy, they're also difficult because you need to really know your in detail, like in between the lines content for you to be able to answer it. All right. So I'm going to give you a minute, less than a minute for each question. In case you're not able to, in case you want me to go back to a question, just tell me which question number it is. What I want you to do is write down just the option number or the option in your paper, and then we'll discuss it at the end. All right. So here's your 30 seconds. Go. Okay, I'm going to the next question. Okay, I'm going to the next question. Okay, next question. Okay, next question. For those of you who've just joined, we are doing MCQs. Kindly read the question, write the answers, and then we'll be discussing them in 10 minutes. Okay, so just write out the options that is there. Please start with the next question because I'm moving on to the next question. Okay, next question. Okay, next question. Okay, next question. And the last MCQ. If there is any question that you missed that you'd like to see the question again, please let me know. Otherwise, I will start discussing the answers and we'll go over it in detail. You can leave a question number in the chat box if there is a question that you want me to, post on the screen again so you can take a look. Nobody wants me to repeat any questions? Okay, let's start discussing it. All right. Question 1. When a magnesium ribbon is burnt in air, the ash formed is white. Can anyone tell me why? You can unmute and answer. Nobody? It's because you guys don't know the answer or you're just too shy to let me know. You can drop it in the chat box if you know. All right, so when magnesium is burnt in air, this is what your reaction looks like. The compound that's formed at the end, which is magnesium oxide, is a whitish color. All right, so therefore, when magnesium ribbon is burnt in air, the ash formed is white. Moving on to question 2. All right, let's take a look at this. Consider reactions calcium plus Ca2 plus OH minus giving you calcium hydroxide. The precipitate of calcium hydroxide will be what color? All right. So you are expected to know that the colored ions are generally compounds of Fe2 plus, Fe3 plus, Cu2 plus. These are the most common ones. Ag plus has a silver color. And I don't think you do manganese, but just for information, manganese has a colored compound. It forms a colored compound. Almost all the other, a lot of the other common ions that you work with, like magnesium, aluminum, calcium, zinc, lead, all right, all of these are going to be white precipitates. All right, so these are the most common colored precipitates that you will see, especially these three. Iron salts form a light green color precipitate or a light green color salt. Fe3 plus forms a reddish brown salt. And copper salts, think of copper sulfate, it forms a blue salt. All right, this has the salts are generally silvery white. All right, and manganese salts are what we call as a buff color, or which is kind of like a skin color that you see. And all of these are white color precipitates. So from this, we know that the answer is white color. So calcium, when it combines with hydroxide ions to form calcium hydroxide, we know there's a precipitate because it's indicated by this state of S, which means it's a solid state. Okay, and the precipitate of calcium hydroxide will be white in color, right? If it was green, it would be Fe3 plus. If it was blue, it would usually be copper Cu2 plus. And if it's, green is Fe2 plus. This would be generally Cu2 plus and brown will be Fe3 plus. Any questions? Great. All right. Next one. This was a pretty straightforward one. When you are writing your equations, you need to make sure that the state symbol, meaning is it liquid, is it solid, is it gas, is it aqueous, all of this needs to be included while the equation is being balanced. All right. So that is the key thing. Next question. Simple balancing. In case you're not familiar with balancing, let me just walk you through it very quickly. So when you're trying to balance, you're trying to make sure that the number of atoms on the left-hand side is equal to the number of atoms on the right-hand side. So you can basically split this, into what are the elements present on the left-hand side and what are the elements present on the right-hand side. Okay. Now on the left-hand side, you can see there's only one aluminum and there is 2 oxygen. All right, we're talking in terms of atoms, which is why we represent this as just O and not O2, because O2 is a molecule. And on the right-hand side, all right, this is LHS. LHS is here, and this is your right-hand side. On the right-hand side, you have 2 aluminum and 3 oxygen. Now, the point is that we can see on the right-hand side, there is more number of aluminum and oxygen, and we need to balance that out with the left-hand side, right? And the simplest way to balance that out in this particular case will be to see what is the least common multiple that we can find between 2 and 3. And the reason we're looking at the least common multiple is because we want something to be able to multiply it by so that both sides can have the same value, all right? Now, for between, if you look especially between oxygen, right? If I multiply this into 3 and this into 2, it will give me 6 oxygen on my right side and 6 oxygen on my left side. All right. Okay. Now, what happens if I multiply aluminum into just 2? Is it balanced? Yes, no, maybe it's not balanced. Okay. All right. So can you help me to balance it out now, aluminum? Anybody want to try?
Multiplied with 4.
Multiplied with 4, right? So what happens when you multiply with 4? Let's write out the entire equation. It makes it easier for you to understand, right? So when we do this as Al plus O2, giving me Al2O3, in front of 2 in front of this Al2O3, my oxygen number is increasing by 4 on the right-hand side, and 2 into 3, my aluminum number is increasing by 4 on the right-hand side, and 2 into 3, my oxygen is increasing by 6. So putting a 3 in front of O2 is enough to balance it by 6. But if I put just a 2 in front of aluminum, it's not going to be balanced, right? Why? Because on my right side, I have 4 aluminum, and my left side, I need to balance it to make it 4. So what I'm going to do is I will write 4 in front of the aluminum. And the question here is, what is the number of moles of aluminum required to balance the equation? So our option is D. Are there any questions? Okay, all right. Let's look at this. Okay, now, an element X on exposure to moisture, reddish brown, and a new compound is formed. So the clue here lies in the fact that moist air turns an element into reddish brown. Now, I'm sure you've all heard of rusting, or you've all seen rusting as well occur. When does rusting occur? Rusting occurs when you have iron, right? Just metallic iron. And this metallic iron, when it is exposed to both water and air, or in the form of moist air. So it doesn't have to be just water as water. It could be air that contains water droplets as well. This, when it combines together, undergoes oxidation, which is basically a rusting. And on oxidation, it forms a compound, which is Fe2O3. This is our rust. Now, I already told you that when a compound has Fe3 plus ions in it, it will be a reddish brown. We just spoke about that 2 slides ago, right? So the clue here is that, oh, I have a reddish brown substance, and that is my compound Y. So Y is reddish brown. Now, from the options given here for Y, the only thing, aluminum is white, CuO is going to be a bluish color, silver is going to be, silver compounds will be a whitish color or a silvery white color. So the only option here is kind of iron, right? And we can ensure that this is right, or we can kind of confirm our own answer by looking at the question. An element X, when exposed to moist air, turns reddish brown. So iron, in the presence of moist air, O2 and water, will turn into Fe2O3. I'm not going to go into the complete equation because this is not complete at all. All right, it's a much longer equation, but this is the this is how you kind of solve for this, or how you analyze and break down this question. The clues are within the question. Always take a second to kind of read the question a second time and see if, and then kind of like pick up on the clues from that. All right. Okay, let's go to the next question. Are there any questions? Do you have any doubts till now? Is there anything that I can stop and repeat? No? Okay. All right. Let's take a look at this. Now, consider this reaction as an example, and the answer is given as A and C, meaning it is a displacement as well as a redox. Now, why is this being classified as a displacement reaction? Because a displacement reaction occurs when you have one element replacing another element in a compound. Okay, so if AB is a compound and C is replacing B in the compound, the product will be AC, right? So this can be considered as a displacement. Why is it not a double displacement? Now, I know that there tends to be a little bit of confusion between displacement and double displacement. For a double displacement reaction, you need to have two compounds, not an element in a compound, which means you need to have something like AB plus CD. All right. So this would be a double displacement. If a reaction occurs between AB and CD, AB is a molecule, CD is a molecule. When they interchange or exchange their ions to form, let's say, AD and BC, this will be called as double displacement. Okay. So double displacement occurs when you have two molecules or two compounds undergoing reaction, and single displacement or simple displacement will occur when you just have a compound reacting with either a homoatomic molecule. So homoatomic meaning one molecule with the same kind of atom. So O2, Cl2, F2, H2, these are all homoatomic molecules. Why are they molecules? Because there's more than one atom in them. Why are they homoatomic? Because they're made up of the same type of atom, right? It is two hydrogens, two atoms of hydrogen that form H2, two atoms of oxygen that form O2. Right? So when you have either a homoatomic molecule or an element reacting with your compound, right? That is when you see a displacement reaction. Now, why is this considered to be a redox reaction? Because we have oxygen specifically being added to the ammonia. Now, oxygen will cause oxidation, and it is known that oxidation never occurs on its own. There is always going to be reduction occurring along with the oxidation for one simple reason. If I'm going to be adding or removing, if I'm going to add oxygen or remove hydrogen, right? When I remove the hydrogen, it has to go somewhere. It cannot just randomly float in space, correct? So that when that hydrogen is added onto another molecule, it becomes reduction. So your oxidation and reduction will always work in tandem. It will always work hand in hand. All right. So this is how you can identify what is the type of reaction that is taking place. Okay. All right. Now let's look at this. Remember, I was talking about the whole idea of observations. This reaction is a beautiful, I mean, this question is a beautiful example for it. Okay. So when you are trying to analyze this type of a question, first read the entire question, highlight what is important. For starters, we have a dilute ferrous sulfate solution. Okay. Now, ferrous sulfate FeSO4 contains Fe2 plus ions, and we know that Fe2 plus ions are light green in color. Okay. Now, to this, we have acidified permanganate added. So potassium permanganate, KMNO4, is a purple color. Okay. Is a light purple. And how do we know this? Because it tells us that the light purple color of the solution is fading. Now, if my ferrous sulfate solution is green, then obviously the only other solution available in the starting is acidified potassium permanganate. So that has to be the purple color, right? And it says that the light purple color will fade and disappear with time. So what that means is, it means that this KMNO4, when it is reacting with FeSO4, it is breaking down to form products of A, B, and C, where none of these are any longer forming colored compounds. All right. So this light green is losing its color. This purple is also losing its color. All right. And that's how we know that we have an oxidation reduction reaction occurring. Now, how do we know that KMNO4 is the oxidizing agent? We know that because potassium permanganate, potassium dichromate are the most common oxidizing agents that you do use, and they will give up their oxygen to the neighboring compound. Okay. Now, how do we know that the color is not disappearing because of dilution? Because we're not adding any water, right? So where is dilution occurring here? It's not. All right. KMNO4 is not an unstable compound, and we know that because if it was unstable, there would be other like side reactions occurring with it. So that is what that is how you know that it is not an unstable compound. Okay. So this is how you can again break down and analyze the answer. All right. Next. Okay. Next question. Solid calcium oxide reacts vigorously to form calcium hydroxide with the liberation of heat. All right. This is called slaking of lime. Now, which of the following is true based upon the reaction that's given above? Now, we know that there is liberation of energy, so it means that it has to be an exothermic reaction. That is for sure. All right. All right. It cannot be an endothermic reaction, because endothermic reactions occur only when you have energy being absorbed, not when energy is being liberated. Okay. Next, the pH of the resulting solution will be more than 7 or less than 7. Now, I know you basically do a lot of the pH concept in the second chapter, which is acids, bases, and salts, but I'm going to hope that you've done it and bring it in here. So our pH basically works as 1 to 7 to 14, okay, where 1 is highly acidic, 7 is neutral, and 14 is highly basic. So we go from highly acidic, less acidic, less acidic, less acidic to neutral. From neutral, more basic, more basic, more basic to highly basic, which is 14. Okay. Now, calcium or any solution that is made from a metal, so calcium hydroxide, sodium hydroxide, potassium hydroxide, all of these metallic based hydroxides will always be basic in nature. Okay. All metallic based solutions will be basic in nature. All right. So that's how we know that the pH of the solution at the end will also be greater than 7, because only when we go from 7 to 14 on the pH scale, we are going from neutral to basic. Correct. And if my solution is going to contain calcium hydroxide in water, then it is definitely going to form a solution which is basic in nature. And if it is basic in nature, then my pH has to be greater than 7. Okay. If it is basic in nature, my pH has to be greater than 7. Any questions so far? Great, almost there. Okay, last 2 questions in this, and then we'll move forward. In which of the given will heat energy be evolved? Okay, now decomposition reactions are usually endothermic, which means they absorb energy. So you can see that electrolysis is a decomposition reaction, so it will absorb energy. Again, decomposition of silver bromide in the presence of sunlight is endothermic. So there's no heat energy being evolved here. Now, between dissolution of ammonium chloride and burning, the minute you have anything that is being burnt in air, undergoing combustion, these kinds of words, there will always be heat energy evolved. Heat is given out along with the process of combustion and burning, etc. All right. So that's why your answer is burning of LPG. Any questions? No? Okay. Great. Next. In the double displacement reaction between aqueous potassium iodide, so we have potassium iodide plus PbNO3. Okay. This forms a yellow precipitate of lead iodide. So we have Pbi that is formed, okay, along with KNO3. Now the color is because of lead iodide. Okay, the color is because of lead iodide. So this means if you don't use lead nitrate, correct, what is the other alternative option that you can use? Okay, to get the same precipitate at the end of the reaction. Now, for lead iodide to be formed, you obviously need lead and you need iodine. So because you definitely need lead, it rules out option C and option D. Okay, the color of the precipitate is because of lead iodide, and the color of the precipitate is not because of nitrate being present, right? There's no nitrate in lead iodide. So that means it doesn't matter if you have ammonium nitrate, and it doesn't matter if you have potassium sulfate, because neither the nitrate nor the potassium are contributing to a color but in any way, right? They're not contributing to the color formation or the precipitate formation in any way. Okay, the other key thing is here, we are told that lead sulfate is insoluble, and you cannot perform a double displacement reaction if you don't have 2 aqueous solutions. You cannot perform a double displacement reaction if you don't have 2 aqueous solutions. Okay, so that automatically rules out option A. So that leaves only option B, lead acetate. Okay, lead acetate is the only other option that can be used when you're performing a double displacement reaction, if you want to still get your lead iodide as your precipitate. Okay, so this brings us to the end of all of the questions of your MCQs. Let's move forward. If there's any questions on what we've done so far, please raise your hand and let me know. Okay, very quickly, let's discuss these questions. So these are the short answers or the very short answers that usually come. And let's look at some simple ways to identify what is the type of reaction. Now, when you are looking A, B, and C, I think C is kind of straightforward. This will be a decomposition reaction. Why is this straightforward? Because we are going from one compound AB and breaking it down to give A plus B. So we're starting with one and we're getting 2 or 3 products at the end. And that is your key characteristic for a decomposition reaction. Start with one reactant and break it into 2 to 3 products. All right. Okay. Now, what about A and B? Now, between A and B, there are 2 reactants on the left-hand side. In A, we have a compound reacting with an element, okay? And in B, we have 2 compounds reacting with each other, okay? Now, remember what we spoke about? When a compound reacts with an element or a homoatomic molecule, the reaction will always be a simple displacement reaction, okay? The reaction will always be a simple displacement reaction. So this will be simple displacement. And when you have 2 compounds reacting where their compounds are interchanging the ions, so you have A coming here and C coming here, you will get CB plus AD, and this will be double decomposition. Okay, double decomposition. Any questions on how to identify the type of reaction? All right, let's look at this. Now, these are the other types of larger, longer questions that come. So let's kind of work our way through as many as we can before we have to end the session at 7. Okay, now, a lot of the questions will have clues within the question itself. So always take a second to read through it more than once. Okay, and you'll really be able to understand better what is happening. Okay, I'm going to give you a second to read through the question. Let's not rush because I want you to be able to also analyze it by yourself. So this is H2S plus CuSO4. Okay, now it tells us that we have the solution of the color fading and a black precipitate is formed. Okay, now I don't know if you know this, but CuS, copper sulfide, is actually a black PPT. Okay, and this combines with SO4 to form plus. Sorry, let me just rewrite that again. These 2 combine to form H2SO4. Okay, not going to give you H2SO4 per se, but we'll just leave it at this for now. Okay, we can see here what is happening. Anybody? What do you have happening here? Is it a double displacement, a single displacement, decomposition? Nobody wants to try and answer. It's a double displacement. Yes. Okay. All right. Now, why is the color of the blue solution fading? Okay, because copper sulfate is being converted into another product, which is your copper sulfide, and it's going from a solution form to a solid form. So this is one of the observations. You have the loss of the blue coloration and the formation of a precipitate, which is your black precipitate. Okay. The chemical name, like I said, CuS, this is called as copper sulfide. All right. And balanced equation. This is your final equation. So you can go ahead to balance it, but it's actually self-balanced. So you don't have to worry about it. Okay. One less thing for you to worry about. But if they say give the balanced chemical equation, you can just write it as it is and mention it is a self-balanced equation. That's more than enough. Okay. Any questions on this? No? Okay. All right. Next, I'm going to be doing quite a few questions with observations because that is one of the things that a lot of people struggle with. So I want to make sure that we cover as much as we can. Let's talk about this. Okay. Now, take a second, read the question. Okay. Any answers? Any guesses? Okay. So have you all heard of something called as the reactivity series, where you kind of have so for displacement reactions to occur. Now, first of all, how do I know these are displacement reactions? Because it says metals are reacting with dilute hydrochloric acid. So that means each of the individual reactions will look like this. HCl plus Ag, HCl plus Al, HCl plus Na, HCl plus lead. So we can see that there is a compound reacting with a simple metal, okay, with a simple metal. So this tells us it is a simple displacement reaction occurring. Now, will all of these reactions occur? No, they won't, especially when it comes to metals reacting with an acid. The metals need to be, there is something called as the reactivity series, where only if the metal is above hydrogen in the reactivity series, it can displace it from an acid, okay. Now, the metals that generally lie above hydrogen are the ones that are highly reactive, like sodium, potassium, aluminum, zinc, lead, etc. Okay, so and the observations that you're seeing here kind of indicate the reactivity series. Okay, so it tells us that the silver metal does not show any change, and this explains to us that it is because silver is below hydrogen in the reactivity series. If silver was above hydrogen in the reactivity series, it will definitely displace it and there will be some kind of a reaction that is seen. But the very fact that it does not displace it, that we're not able to see a reaction from it, indicates that it lies below hydrogen in the reactivity series. Okay, right. Now, what is the second process? It says that the temperature of the reaction mixture rises when aluminum is added. So why do we see the entire reaction mixture having an increase in temperature? Because this is an exothermic reaction. Okay, and this also indicates that obviously aluminum lies above hydrogen in the reactivity series. All right. Okay, let's look at the third observation. The reaction of sodium metal is found to be highly explosive. Now, only metals that are super reactive and lie right at the top of the reactivity series will be highly explosive. So we know that sodium is super reactive. Okay, extremely reactive, lies at the top of the reactivity series, and that is why it is able to behave in a very explosive fashion. Okay, and the last one, why do we see certain bubbles coming out from this lead reacts with acid? Because when lead reacts with acid, it will displace hydrogen in the gaseous form. So you'll see bubbling of the hydrogen coming out of the liquid. All right. This is your observation. Now, one more interesting thing about this observation is that this bubbling doesn't continue for a long time. It kind of stops in between, because after a period of time, your metal, the lead metal, kind of gets coated, and it gets coated with an unreactive coating, and it stops taking, like the reaction stops taking part. Okay, so so this product, I mean, if you want a complete reaction for this, let me just give it to you. So you have it down, PbPbCl2 plus H2. This would be your overall reaction for this particular question. Are there any questions? Everyone is fine? Wonderful. Okay. All right. Can I move on to the next question? Yeah. All right. Let's look at this. 2 grams of ferrous sulfate crystals are heated in a dry boiling tube. What are our observations? Take a second. Think about what I've given. Okay, right. So this is ferrous sulfate, and they are telling us that you're just heating it. So obviously it is going to be a decomposition reaction, a simple decomposition reaction. Okay. Now, what are our observations? Like we spoke about a little earlier, your ferrous sulfate happens to be a light green color salt. So the first observation, anybody want to take a guess what's going to happen to the color? Anybody want to take a guess what's going to happen to the color? Is it going to remain? Is it going to change? Oh, I'm sorry. Is it going to remain? Is it going to change? Been talking about this for a while. Someone want to try?
It'll turn reddish brown.
Reddish brown. What is your product?
Fe2O3.
Very good. Yes, perfect, actually. Okay. All right. Do you also know what else is happening? What are the other products of it? Anybody want to try what are the other products of it? No? Okay. Let me go ahead and give you an equation. Yeah? Okay. All right. So our equation will be Fe2O3 plus SO2. Okay. And I think you also have SO3 given out. You have SO3 given out. Okay. Let's just balance this so that we can save a little bit of time. Okay. Now Fe2O3, also called as ferric oxide, is a reddish brown color. Okay. So our first observation is the change in color from a light green color to a reddish brown color. Okay, that's the first thing. Now, there's a step in between that occurs. For ferrous sulfate to be in the form of crystals, it needs to be hydrated. Now, only hydrated ferrous sulfate or ferrous sulfate that contains what we call as water of crystallization is going to have this light green color in it. Okay. Once this is heated, the first thing that will happen is loss of your water of crystallization, and it will become anhydrous ferrous sulfate. And anhydrous ferrous sulfate is actually white. So from white, it will then become your reddish brown. So once it decomposes further, it will become reddish brown. So I think we've kind of listed all of we've written all of the answers for this question in this one particular thing. A second observation would be sulfur dioxide is evolved, and sulfur dioxide is also a colorless, odorless gas that will tend to turn, that can also turn lime water milky. Okay, so you can, it also has a bleaching property. So that could be also something that you can talk about. So yeah, these would be your observations for what happens to ferrous sulfate crystals when heated. Okay. Any questions? No questions? Okay, I think we have time for one more and then we'll probably stop. Yeah, just 2 questions left. Great. Okay. All right. So let's take a look at this and stop with this because I feel we've done a lot of ferrous sulfate questions anyway. So let's take a look at this, and then if there's any other general questions from all of you, you can ask me or we can end the session with this. Okay. All right. So take a second, read the question, and then we will discuss it. I don't want to just directly jump into discussing it. All right, let's go. So it tells us that we have an aqueous solution of some metal nitrate P. So we have PNO3, we don't know what P is. This is reacting with AgBr to form a yellow precipitate of Q that is used in photography. Okay. And Q on exposure will decompose to form the metal found in P and a reddish brown gas. All right. So what are our clues here? I'm sorry, just give me one. Yeah, sorry. Anyone want to go ahead and give me the answer for this, considering that we've discussed this quite a bit till now? No? Nobody wants to try? Promise I'm not going to eat you up.
Ma'am, let me try.
Yeah, please try.
Sodium bromide plus silver nitrate gives rise sodium bromide and yellow color precipitate plus sodium nitrate.
What is the yellow color precipitate again? So you're telling me this is sodium nitrate.
Yeah.
P is sodium nitrate. Okay, so that will give us sodium.
No. Sodium bromide plus
Oh, I'm sorry.
silver
I
nitrate.
wrote as silver. Yeah, silver nitrate. Correct. I wrote the other one. I wrote as AgBr instead of silver. I'm sorry. My bad. Absolutely right. Silver nitrate plus
Sodium
again,
bromide.
I'm writing silver all the time. I'm obsessed with silver today. Never mind. Silver nitrate plus sodium bromide, absolutely spot on, will break down to give you a silver bromide plus NaNO3. Just realized I gave away the answer right in the beginning. Silly me. All right. Now, Q on exposure will undergo decomposition. So your AgBr will undergo decomposition and you will get Ag plus Br2. Now, in case you didn't know, bromine also happens to be a reddish brown gas, which is like, I don't know if you know another reddish brown gas. Are you guys aware of another reddish brown gas? Anyone? Do you guys know that NO2 is also a reddish brown gas? So if you have a nitrate heated and it breaks down to form NO2 gas, NO2 gas is also a reddish brown gas. So yeah, there you go. All right. So this is your overall reaction. Silver nitrate plus sodium bromide, perfectly correct. This is self-balanced, so you don't have to worry about balancing it. And this is a great example for a double decomposition reaction. All right. Okay, so this brings us to the end of the session. We've gone over, so I focused a lot on the observation style questions because, you know, over the years, I've seen that's something that a lot of people tend to kind of get stuck with, which is why I wanted to focus on that. But let me know if there was, if you have anything else specifically. We have like another 5 more minutes that we can quickly go over. If there's anything else that you guys want to ask, please, now is the time. Unmute and ask. Give me a second. I'll stop the recording so you can ask without feeling shy.